All right, welcome. Every smart device you have, from your car to your thermostat, is constantly listening to the physical world around it. So today, we're going to decode the invisible language that actually makes this whole conversation possible.
Or, how does your smart thermostat just know when to turn on the heat? Well, it's not magic, not really. It's this brilliant process that starts by listening very, very carefully to the world around us. At the end of the day, it's really just a translation problem. How do you take a physical reality, something like heat or pressure, and turn it into the language of electronics? The answer? Well, it's all about electrical signals. And that whole process, that translation, it actually has a name: signal conditioning. It's this super important kind of invisible step that takes a messy, raw signal and turns it into something a computer can finally get its head around. So let's break down how it all works. Okay, so our journey starts with the sensor. This is a device that's designed to capture a little piece of the real world and, turn it into a tiny electrical pulse. And believe me, sensors are everywhere. I mean, they measure just about anything you can think of, from the speed of a wheel to the chemical makeup of a liquid. For pretty much any physical thing out there, there's a sensor that can convert it into a small electrical signal. Okay, but here's the problem. This raw signal, it's nowhere near ready to be used. It's super weak, it's full of what we call electrical noise, and honestly, it's in a format our devices just can't speak. It's like trying to hear a faint whisper in the middle of a hurricane. So, what's the very first thing we have to do? We've got to make that whisper loud enough to actually hear. And that's where the amplification stage comes in. Yeah, this is probably the best way to think about it. Amplification basically takes that tiny, faint signal and just cranks up its strength, or its amplitude, so the rest of the system has something real to work with. And the little hero component that makes all this magic happen, it's called an operational amplifier, or what everyone just calls an op-amp. Seriously, this little circuit is the absolute workhorse of signal conditioning. It takes that tiny voltage from the sensor, multiplies it by a huge factor, and spits out a much stronger, much more usable signal. Now, op-amps can be set up in a couple of basic ways. A non-inverting amplifier boosts the signal and keeps its polarity, whether it's positive or negative, exactly the same. But an inverting amplifier, it also boosts the signal, but it flips that polarity. Why the difference? Well, it really just depends on what the next part of the system needs to see. All right, so our signal is loud now. Awesome! But there's a new problem. See, we didn't just amplify the good part of the signal, we amplified all that junk, all that noise, right along with it. So now we gotta clean it up. So this is what we're looking at. An amplified signal, yeah, but the important info is buried in all this interference. We didn't just turn up the volume on the voice, we turned up all the static too. And this is the magic of filtering. A filter circuit is specifically designed to just strip out all those unwanted frequencies, all that noise, and let the important signal pass right on through. What you're left with is a clean, smooth signal that actually represents the original measurement. So much better. Okay, so filters basically come in two main flavors: passive and active. Passive filters are the simple ones. They use basic parts to get rid of noise, but they can't add any energy back into the signal. Active filters, though, they use an external power source, and that lets them do much more complex filtering, and they can even boost the signal while they're at it. Okay, so we've got a strong, clean signal. We're almost there. But it's still an analog signal. Think of it like a smooth, continuous wave. The problem is, our computers, they just don't speak that language. So it's time for the final and maybe most important translation. And this is the fundamental difference we have to bridge. The real world is all smooth and continuous. That's analog. But computers are digital. They can't handle an infinite number of values. They need everything chopped up into distinct, countable steps, ones and zeros. And this is where the analog to digital converter, or ADC for short, comes into play. It bridges this gap with a really clever two-step process. First, it quantizes the signal. The best way to think about this is like laying a grid over that smooth wave and then snapping every point on the wave to the nearest line on the grid. Then it encodes each of those lines with its own unique binary number. Now, how good this final digital picture is depends on a couple of things. First up is resolution. This is basically the number of steps or, those grid lines the ADC has to work with.
For example, an 8-bit converter gives you 256 steps, but a 16-bit one, that gives you over 65,000. So more bits means way more detail and a much more accurate conversion. The other big factor is the sampling rate. This is all about how often the ADC takes a measurement, like a little snapshot of the analog signal. If you've got a slow-changing signal like the temperature in a room, a slow rate is totally fine. But for something that changes really fast, like an audio signal, you need a super high sampling rate to capture all that detail.
And there's a really, really important rule here. It's called the Nyquist rule. Basically, it says your sampling rate has to be at least twice as fast as the highest frequency in the signal you're trying to measure. If you sample too slowly, it's not just that you miss some details, you actually create a completely messed up digital signal. It's an error called aliasing. It's kind of like when you see a video of a helicopter's blades and they look like they're spinning backwards. Same idea.
And just like that, our journey is pretty much complete. We've successfully taken that faint, noisy whisper from the real world and turned it into clean, structured digital data that a computer can actually understand. So the big question is, what can we do with it now? Well, pretty much anything you can think of. This digital data is now the language of action. It can pop up as a number on a display, it can be logged into a file for later analysis, or it can even be sent as a command to control something like a motor. It completely closes the loop between sensing the world and then acting on it. So let's just quickly recap that whole journey. It all starts as that raw, messy whisper from a sensor. Then the amplifier makes it strong, the filter cleans it all up, the ADC translates it into digital data, and finally, a computer or processor turns all that data into something useful, information we can see or even in action in the real world. You know, this whole process, signal conditioning, it's really the invisible foundation of our entire data-driven world. It's how our technology listens. And as our tech gets better and better at hearing the world with this incredible clarity, you just have to wonder, what kind of new conversations are we about to start having with our machines?